So what we have is the naturally abundant element of nitrogen in our atmosphere, and that obviously can interact with a neutron, shall we say, um, from these cosmic rays. So it's actually, we've got protons coming in, but I mean, cosmic rays are made of all sorts, okay, of subatomic particles and so on, alongside your standard radioactive particles. But bear in mind, what I want you to remember back of your minds is Einstein's famous equation here, where we have mass and energy interchanging, and the thing is with cosmic rays, you can view it, as a wave, in the sense that light we can view light as a wave, or conversely light as particles. But the idea is there is obviously kinetic movement energy or light energy that comes with these cosmic rays. So therefore, that light energy, or whatever type of energy it has, can be converted into mass, right? So at any point in time, this this energy can change into mass and into different forms of masses. And obviously, in our last topic, last chapter, when we were talking about the subatomic particles, leptons, quarks, and so on, we looked at some of these fundamental particles. And sometimes, for split seconds or small amounts of time, that energy can turn into neutrons or protons. This is one specific example, okay? But for a small portion of time, these can exist, by themselves temporarily, okay? But they're very unstable, and then they can flip back to energy as easily too. But the idea is a proton can hit particles or atoms in the atmosphere, and likewise neutrons can hit particles in the atmosphere. And if they hit a nitrogen atom, okay, so this is the mass number of a nitrogen atom, 14. It's got 7 protons. This reaction can take place, and actually we can produce this isotope of carbon, okay? And this isotope of carbon, known as carbon-14, is an unstable isotope, okay? So this is the unstable isotope, okay? And a bit of GCSE recap. Well, you should know, I'm sure, isotope are elements or atoms of the same element with different mass numbers. So they've got either more or less neutrons, but they've got the same proton number. Okay, so a carbon-12 atom, which is our more stable atom here. There's actually carbon-13 too, but less abundant. It's a less abundant isotope, but carbon-12 is the most stable one isotope. And I was going to say 14. Yeah, so obviously we've got excess amount of neutrons here, but we get a proton being emitted in this reaction as a result. But and bear in mind, this is a rare reaction here, right? This doesn't take place every single day. This only happens in the upper atmosphere. Okay, I mean, yes, we can recreate this technically in a particle accelerator, but we need, first of all, high energy, where the mass and energy interchange regularly, so we get the emergence of these neutrons or protons for this even to occur. Okay, but you can see anyway the numbers balance out, don't they? So this is conserved, 0, 7, and we got 6 plus 1 here. Okay, so we're not losing any of our the proton number is being conserved there. Likewise, look at our mass number. Okay, so this reaction is perfectly acceptable, theoretically acceptable. Now let's see what happens now. The reason why we know carbon-14 is unstable is because we can observe this reaction here. So we can have carbon-14 decaying into back into nitrogen, and a negative electron, so it's beta minus decay, occurs. Okay, so this should be slightly familiar to you. We know that a beta minus particle will be accompanied by an electron, anti-electron neutrino. Okay, again, the atomic numbers are conserved here. 7 minus 1 equals 0, and obviously this is 0 here. Mass numbers are conserved. So if we look at what's happening, or historically, or every single day with cosmic rays, this process, we get nitrogen being converted into carbon-14, but the opposite is occurring too, because we know carbon-14 can decay back into nitrogen. So we're effectively not losing. The general amount of nitrogen in the atmosphere is staying the same, okay? Because it's a reversible reaction. Now, how does this process come into carbon, what we call radioactive carbon dating? Okay, well, you know in your biology, don't you, that carbon dioxide. So quick recap of photosynthesis. So carbon dioxide plus water. So only plants can do this process. But the general idea is, what do plants do? They intake carbon dioxide, and carbon is obviously one part of your carbon dioxide molecules. So if the plants absorb this carbon-14 isotope, okay, I mean they can obviously absorb carbon-13 and carbon-12, your stable isotopes, okay, but the idea is, in everyday life, you know, biologists or physicists or archaeologists, in fact, you can take the archaeologists out for now. We'll come back to them. But if we take just a normal sample of a plant, we can actually measure the ratio of carbon-14 to carbon-13 to carbon-12 inside that plant. And if it's living and we compare it with other living plants, the ratio should be the same. Okay, so let's write that down. So all living organisms, and I'm going to include animals here because animals eat plants, and therefore their levels of carbon-14 to carbon-12, the ratio will also be constant provided they're living, and that's the key thing there. So all living organisms will have a certain ratio of carbon-14 to carbon-12 isotopes in okay, so if we were to, you know, check and bear in mind, animals, if they're living, they're constantly eating plants and so on, or if the animals eat other animals, you know, the concentration of those plants will remain the same. Okay, so we can actually check this ratio, and on average it should be the same across the different species, provided they're living. However, the key thing when it's a dead organism, okay, so the next point, however, in a dead organism, new plant matter, okay, has not been digested okay, so this means so there's going to be less carbon-14 as this as this will have decayed without being replenished. Okay, sorry, that's small replenished. Okay, so I'll just read that out. So what do we have here? So in dead organisms, they're no longer eating new plant material, or if it's a dead plant, that plant is no longer photosynthesizing. Therefore, it's not intaking any new carbon atoms. Okay, so that includes carbon-14, the isotope, and therefore, as soon as it dies out, the carbon, what's left inside the matter, the body, the tissue of the organism, that is obviously going to decay, isn't it? And that's how we can compare. So we can compare the ratio of this carbon-14 isotope in a dead plant of a known species, and we compare that with a living plant of the same species. And what we're going to be looking at next is the equation for that, which is the activity equation or count rate equation, and yeah, and we can work out the time period with which how long that organism has died. Okay, so it's obviously it's an approximation. There's lots and lots of assumptions. We're assuming that the amount of we're assuming this process right here at the start with the cosmic rays here, this was occurring at a frequent rate. So for example, let's say, I don't know, 2,000 years ago, we're assuming the rate at which the nitrogen and the carbon were transforming into one another is the same in 2021. That's a big assumption, obviously, but that's all we can do. So therefore, there's a caveat and there's an error when scientists in papers or archaeologists give or quote numbers. I don't know, certain artifacts are believed to be, I don't know, 30,000 years old. There's a plus or minus sign there as well, okay, just to account for the error in this radioactive carbon dating, okay? So yes, it is a powerful tool in terms of giving us a rough estimate of certain times, okay, or potential dates for objects. Okay, I'm now going to, let's look at the equation now for this carbon, radioactive carbon dating. Okay, so you should now see the textbook, and I'm just going to go through this example here. Okay, so we've got a wooden axe found in an Egyptian tomb. It's found to have an activity of 0.38 becquerels. The activity of an identical mass of wood, again, we're assuming it's the same type of wood, cut from a living tree, is 0.65 becquerels. Okay, so obviously it's got a higher activity. We've got a greater amount of carbon-14 here, as it's fresh. Okay, it's just photosynthesized, the previous day, and so it's got more carbon-14 content, whereas the older one in the tomb, it's got less, and we can see that because the activity is a lot lower. Calculate the age of the wood used to make the axe. Okay, so I said, yeah, we're going to start off with this. Several things to note down. It's not given in the question, but earlier on, the half-life of carbon-14 is 5,700 years, which should be here somewhere. Here we go. Yeah, half-life is 5,700 years. Okay, so that's a bit of data that's going to be important to us. Okay, so let's put some of these numbers down. So we have log 2 over our half-life, which I said is 5,700 years, but we want it in seconds, so the conversion is times 3.16 times 10 to the 7. Okay, which will give us a decay rate or decay constant of 3.85 times 10 to the minus 12 per second. And this is really useful now, because now if you think back to this equation, the activity at any given point in time is equal to the initial activity A naught to the power exponential negative of the decay constant, which we just worked out, times the time period. Okay. Now you can see there's only one unknown here, and the unknown is the t here, right? And that's what we want to find out. Okay, it's asking us calculate the age of the wood used to make the axe. So we're going to have to use some logs, but before I do that, let's put what we know. So the activity of the sample is 0.38, and it had well, we're assuming it had an original activity of 0.65, big assumption, but it's the same type of living tree. We're assuming same species, so let's put that in our calculation. So we have 0.38 is what we've observed. Our living tree at the moment is 0.65. And I'm going to put my decay constant in there. So it's 3.85 times 10 to the minus 12. Okay, and then times t, right? So t is our unknown. I'm going to log both sides. In fact, before I do, let's just let's divide 0.65 to both sides. So it's 0.38 divided by 0.65. And that will give us just the exponential. Okay. So now if I log both sides, I can now get rid of this exponential sign, and it should look something like this. So the e disappears, and I'm just left with minus 3.85 times 10 to the minus 12 times t. All I've done, the log just cancels out the e, and you're left with this. And it's just a matter of making t the subject, so therefore t is equal to log 0.38 over 0.65 divided by negative 3.85 times 10 to the minus 12, okay? And if you did that in your calculator, should get 1.4 times 10 to the 11 seconds. And if you divided that by divided it by 3.16 times 10 to the 7, to convert it back into years, you would get approximately 4,400 years. Okay, so we have to say we have to assume that the amount of carbon-14 isotopes in the atmosphere did not change much from the time of the Okay, so I've said the assumption is the amount of carbon-14 in the atmosphere is pretty much the same today. Okay. Another assumption is we have to assume that the species of that particular sample is indeed exactly identical to the sample back then. Okay. We have to assume the organism was uh,
Okay, and the final assumption is that the activity of the species that we're recording from now should have been the same type of species back then. And again, it's a big assumption, but it's the only thing we can do in order to make the comparison.